In this video, you will learn to interpret the proton NMR spectra to deduce the structure of organic molecules. To interpret, you will understand what is a chemical environment of protons and its relationship with the number of signals in the spectrum. What is integration, chemical shift, and what are splitting patterns. A detailed explanation of the HNMR spectroscopy is not required at this stage. What you need to know is how the spectra is used to determine the structure of the organic molecule. Let us first understand what is the chemical environment of protons and its relationship with signals in the spectra. The proton NMR spectroscopy is a powerful technique used to determine the structure of organic molecules. The hydrogen nucleus, which has only one proton, have a property called nuclear spin. In the presence of an external magnetic field, they produce signals in the spectrum depending on the chemical environment of the proton. We should be able to predict the number of signals in the HNMR spectrum depending on the number of chemical environments. For example, in this molecule of methoxymethane, the protons on carbon 1 have no neighboring protons or hydrogens because the carbon is attached to an oxygen. It is exactly the same for the protons on carbon 2, where the carbon is attached to an oxygen and they have no neighboring protons. In other words, the 6 protons on this molecule have exactly the same chemical environment, so you should expect just one signal in the spectrum. And here's the HNMR spectrum of methoxymethane with just one signal. But for a molecule like 1-propanol, the protons on carbon 1 have 2 neighboring protons on carbon 2, while the protons on carbon 2 have 3 neighboring protons on one side, which belong to carbon 1, and 2 on the other side, which are attached to carbon 3. So they have a different chemical environment to the protons on carbon 1. In carbon 3, they have different chemical environments, 2 protons on one side and 1 oxygen on the other side. 1 proton is attached to the oxygen, so its chemical environment is very different from the protons attached to the 3 carbons. So you should expect 4 different signals in this spectrum, and this is the HNMR spectrum of ethanol. Now in the workbook, you'll get to practice questions on identifying chemical environments and predicting the number of signals in the spectra. Another clue you can get from the spectrum is the ratio of protons in the molecule. This is from the area under the signal, also referred to as integration. Integration tells us the ratio of protons by measuring the area under the peak of the signal. Note that the ratio of the proton is given by the height of the integral, not the height of the signal. Also note that it's the computer that generates the height of the integral. So here you can see the integral signs. For a molecule like chloroethane, carbon B has 3 protons, carbon A has 2 protons. And you can see that integral B is 1.5 times higher than integral A. This indicates that the ratio of protons is 3:2. Now for bromopropane, the height of the integral B is 6 times the height of integral A. This means the ratio of protons is 6:1. Now this is the case of 2-bromopropane, where 6 protons have the same chemical environment and 1 has a different chemical environment. The position of a signal along the x-axis of the proton NMR spectrum is known as the chemical shift. Protons in different chemical environment, also known as non-equivalent protons, produce signals at different chemical shifts. In a HNMR spectrum, the absorption of protons in tetramethylsilane is assigned a value of 0 parts per million on the scale, and the chemical shift of the other protons are reported relative to TMS. So in the graph, TMS would have a chemical shift of 0. In most organic molecules, proton chemical shifts fall between 0 and 12 parts per million relative to TMS. For example, in chloroethane, the protons on the methyl group have a chemical shift around 1.7 parts per million. However, the protons next to an electronegative element like chlorine have a higher chemical shift, and this is because of chlorine, they experience a stronger magnetic field. In high-resolution proton NMR spectrum, the signals can split into distinctive patterns. The signal is split up by neighboring hydrogens of a different chemical environment. The number of lines in the splitting pattern follows the n+1 rule, where n is the number of neighboring hydrogen atoms. For example, this is the proton NMR spectrum of ethanol. The protons have 3 different chemical environments. Therefore, there are 3 signals. However, signal C in high resolution is split up into a triplet because it has 2 neighboring hydrogen atoms on carbon B of a different chemical environment. Signal B is split up into a quartet because it has 3 neighboring hydrogen atoms on the methyl group, and n+1 would be 4. Signal A is not split up because the proton does not have a neighboring hydrogen. Pascal's triangle can be used to determine the number and relative intensities of the peak. If a proton does not have a neighboring proton of a different chemical environment, then it does not split up. It's called a singlet. If there is one proton which is of a different chemical environment close to it, it will split up into a doublet. If there are 2 protons, triplet, and this goes on, and there could be even 6 neighboring environments, so it will split up into 7. So in the workbook, you'll get to practice questions where you can deduce the structure of organic molecules based on these concepts. So good luck and enjoy.